All right, thank you everyone for coming to the Graphs and Matroids seminar. Today I'm excited to introduce Geoff Whittle, who will be talking about monotone orders of connectivity functions. Thank you.
Okay, thanks, Rose. All right, so before I get underway, I was just telling Rose, the original abstract I had was exactly what you would have seen, except it had a line to the effect of, I don't know whether these are interesting, I'll let you decide. And Rose thought that that was just an extraneous comment that I put in the email to her, so she didn't put it in the abstract, and that was very wise of you, probably, Rose. But in fact, that in a way, it was meant to be part of the abstract, and in a way, that's what I would like this talk to be about, is to whether I'm talking about something interesting or not, and there's all sorts of interesting things going on that I will say unambiguously are interesting, but whether this way of framing things as an interesting way of framing things is the sort of thing that we'll come to at the end. Okay, so what am I talking about? So my first crisis of the day is that I've got to find a way of, all right. Okay, so what's a connectivity function? A connectivity function, so you've got some set S together with a set function on S that takes integer values on all subsets of S. And we say it's normalized if it takes value 0 on the empty set. That's just a convenience thing. The important properties is that it's really a symmetric function, so that the value of its value is not changed under complementation. And the crucial property is that it's submodular. And that will say that's a connectivity function on the set S. And sometimes I'll say S is the ground set of the connectivity function and something like that. All right, and so it's a little bit hard for me to have a sense of who amongst you is sort of familiar with this way of thinking about things. But vertex connectivity functions in graphs, vertex connectivity in graphs can in essence be captured by such a connectivity function. It depends on how you approach vertex connectivity in graphs. There's numerous more or less equivalent ways of defining vertex connectivity in graphs, but if I just take subsets of the edge set, and so now for vertex connectivity, I will obtain a connectivity function on the edge set of the graph, which is the first thing that's slightly weird if you're not used to this. The vertex connectivity it comes from thinking about the edge sets of the graphs. And what you do is you just, for a given subset of edges, you just let lambda x be the number of vertices incident with both x and e minus x. Or else you can think of that, choose your favorite subset of edges, and then the vertex boundary of that set is the set of vertices that are incident with that set of edges and the complement, and that gives a connectivity function on the edges of the graph. That may not be how you describe vertex connectivity normally to yourself, but in fact, this does capture vertex connectivity. And so, and just a little thing about how we could alternatively have defined that is that I could have said lambda x is, for x as a subset of edges, is just the cardinality of the vertices incident with x plus the number of vertices incident with complement minus the cardinality of the vertices altogether. I'm just saying that because that'll be a similar way that we'll see that these connectivity functions can be defined. So there's a connectivity function associated with vertex connectivity in graphs. Edge connectivity in graphs can be captured in a similar way, but we do the reverse thing. We take, so now we get a connectivity function on the set of vertices of the graph, and we just let lambda x be the number of edges joining a set of vertices to its complement. And that's just what you work. It's just an easy thing to see. You just partition the vertices and you look at how many edges are going from one to the other. And it's, you could sort of use the language of cuts, but of course, you know, there's a question of how precisely cuts are defined. So I prefer not to use that language. All right, and we can do a similar thing. We can say, oh, okay, for a set of vertices. Lambda x is just the number of edges that meet that set of vertices plus the number of edges that meet the complement minus the total number of edges altogether. So there's another connectivity function that captures edge connectivity in graphs. So there's two interesting connectivity functions straight away. Matroids and polymatroids. And I think it probably depends on the type of matroid theory that you do, but the type of matroid theory that I do is definitely the case that the connectivity function plays an incredibly important role. So then, and it's sort of, if I sometimes think about what I would do if I were writing a book on matroid theory. I mean, we have James's book, which is awesome, but if there really is space for a whole bunch of new books on matroid theory that could sort of more or less take a sort of a very biased spin. And my biased spin was I'd define a matroid, and then on page 2 I'd define the connectivity function, and that would be the sort of very first thing. So that would mean my matroids would be defined by the rank axioms most naturally, and that would. But in any case, that's so. So the connectivity function is it's just defined in a way that is similar to the way we define vertex and edge connectivity, but we're using rank. And so we're saying the connectivity of set X is the rank of X plus the rank of the complement minus the rank of M. What's this thing measuring? Well, what's actually happening is if you imagine a matroid as a set of points in some high dimensional vector space, perhaps, and you look at it, and how does one get connectivity in a vector space? One gets connectivity in a vector space by linear combinations. So if I want to say some vector is reachable from other vectors, it can be expressed as a linear combination of other vectors. So what this expression is saying is, what's the connectivity of a set X of elements in a matroid? You're really talking about how well connected that set X is to the complementary set of elements. And then you have to say, well, okay, so what you're actually looking at is the rank of the span of X, and you take the span of the complement, and that's measuring the rank of the span of the intersection of those two spaces. And the higher the rank of the span of the intersection of those two spaces, the better connected X is to its complement. Because if the rank of that was 0, then the matroid would be a direct sum, and there's no communication at all between X and its complement. So that is genuinely a natural way to express connectivity in a matroid. One has to think about it and digest it for a while, but it's definitely the right thing. Just sort of incidentally, but I think it's interesting. You could say, how much information about the matroid do you get from the connectivity function? And Manuel Lemos proved the theorem, which I think is a very nice theorem. It's actually a significant generalization of a theorem of Seymour's, who considered the same problem for binary matroids. And he said that if I give you a connected matroid, and so long as the rank is not equal to the co-rank, so it's, sort of the rank is, the cardinality is not equal to twice the rank, is another way of saying that, then we can recover the connected matroid, we can recover the rank function of the connected matroid up to duality from its connectivity function. And that's a very nice theorem. But what happens, so this is a bit of an aside for those of you who know about this sort of stuff. What happens if the rank's equal to the co-rank? So first of all, if you're not familiar with what I'm talking about, just switch off for a few moments and come back, because it's irrelevant to the rest of the talk. But I just want to take an opportunity to pitch this. What goes on when the rank's equal to the co-rank? Now, if you know about spikes, what can happen is, so spikes are examples of matroids whose rank is equal to the co-rank. And spikes, you have these transversal sets that can be either bases or circuit hyperplanes. Now, if I take a spike and I find a transversal set that's a circuit hyperplane, such that the complement of that transversal set is a basis, then what I can do is I can turn the circuit hyperplane into a basis and the basis into a circuit hyperplane, and I haven't changed the connectivity function. I haven't changed the connectivity function. Right, and that's just an example from a specific type of matroid. But what I'm doing is simultaneously turning a circuit hyperplane into a basis and a basis into a circuit hyperplane, and doing that does not change the connectivity function. That gives us examples of two matroids that are different that have the same connectivity function. And if I call that that operation, I'll call that operation a switch, then I think it's essentially equivalent to a conjecture of Manuel Lemos's, but some time ago, I conjectured that if you give me two matroids with the same connectivity function, then up to duality, you can get one from the other by a sequence of such switches. If it were true, it'd be lovely to prove. But it seems to be a difficult problem. So okay, back on track. Forget about that if you don't know about spikes and things like that. All right, so we have the connectivity, back to the connectivity function of a matroid. A polymatroid is something that's exactly the same as a matroid. You just have essentially the same rank axioms, except you don't insist that the rank of a singleton is 0 or 1. Singletons can have rank as an arbitrary integer, or even non-integral values, but from this talk, it's better to think of polymatroids as being integer polymatroids. And you can define the connectivity function of a polymatroid in exactly the same way. And here's a theorem, is that I remember years ago when I was working with Jim and Bert, and we realized that a lot of what we were doing was really just talking about properties of connectivity functions of matroids rather than matroids themselves. And then we had a discussion about just how general are connectivity functions. And because you've just got a connectivity functions, a symmetric submodular function. We had all of these examples, but we didn't know how general connectivity functions were in themselves. And Susan Jout, when she was a master's student of mine, eventually managed to prove this theorem, that every connectivity function is the connectivity function of a polymatroid. So in fact, polymatroids, from the point of view of connectivity functions, polymatroids are fully general objects. So, well, now you have to ask, given that that's sort of the theme of what I'm talking about is how interesting something is, you look at a theorem like that and you say, is that theorem interesting? Well, yeah, it's definitely not. It has some interest for sure. I have to believe it's interesting, but just how interesting is it? And then that theorem made me think of another theorem. Remember when I was an undergraduate when I first did a course in group theory, and probably within about the first 6 or 7 weeks, we managed to prove Cayley's theorem, which says that so we start off by defining groups abstractly, and eventually we prove a theorem which says that every group is isomorphic to a group of permutations. I thought at the time that was an incredibly interesting theorem, and it's certainly not a boring theorem. But how interesting is it? Well, in fact, it's not that interesting. And why is it not that interesting? It's because there are many, many, many different groups of permutations that give you the same underlying group. And so you might think that you gain something from Cayley's theorem by taking your favorite group and then interpret it as a group of permutations, and that somehow helps you. But it doesn't. It doesn't. And in fact, the history of group theory is the other way around. In the 19th century, mathematicians at the time were studying permutations, and they had this odd phenomenon that very, very different sets of permutations seem to have underlying similarities, and that's what led them to actually eventually find the group axioms. Okay, but that's a diversion. I'll move along. All right, so and I think that's a bit the same with that result about every connectivity function being the connectivity function of a polymatroid. it turns out there are many different polymatroids that can give you the same underlying connectivity function, which is different from that result about matroids. So that if you give me a connectivity function, I can find heaps of polymatroids that will have that as its associated connectivity function, but up to some small perturbations that we don't understand yet. If it's a matroidal connectivity function, then the matroid's basically unique. All right, so what now to sort of, so that's a brief overview of connectivity functions and where they come from and why we, but what was it that really stimulated my interest in connectivity functions? And what stimulated my interest in connectivity functions, this probably goes back about 20 years now, when I was working with Jim and Bert and we were studying branch width. And so many of you will already know what branch width is, but in case you're not familiar with branch width, and if you're primarily interested in graph theory, you'll almost certainly be familiar with tree width. Branch width is something that's qualitatively the same as tree width, in the sense that the class of graphs has bounded branch width if and only if it has bounded tree width. But it's approached that a little bit differently, and perhaps from a graph theorist point of view, a bit less naturally, but it's not unnatural, and it's got a certain underlying simplicity that I like a lot. So here's a picture that I managed to skive off the internet. I finally found one that I liked. So a branch decomposition, here's, I'm giving the example for graphs, but a branch decomposition of a graph is a cubic tree, and that's just a tree whose vertices have either degree 3 or 1, whose leaves are labeled by the edges of the graph. So in that there, I've labeled the leaves by the edges of the graph. Well, I haven't, someone else did for me, but I managed to skive the picture. The leaves are labeled by the edges of the graph. And then what I do is I have numbers. And so the thing on the right-hand side is the actual branch decomposition. And then I have to say, what's the width of that branch decomposition? And each of the edges of that tree has got a number that is not inserted there. And when I delete an edge of that tree, what that does is it induces an associated partition of the edges of the graph into 2 parts, and that will have a certain connectivity. So, and if you just check that for those things, you'll find that every time you do that, the connectivity of the associated edge partition of the graph is always less than or equal to 2, I think. So for example, if I look at, say, just as a very simple example, if I look at 2, 3 on the left and I look at the edge that separates 2, 3 off, and I look at 2, 3 in the graph, that induces a vertex cut of size 2. So I put a 2 on that edge. And you would go through and you looks like you've run through with 2. So that's a branch decomposition of width 2. The branch width of a graph is the minimum. I mean, you can make all sorts of branch decompositions, and some of them will give you much bigger numbers because there are obviously edge partitions of that graph that give you connectivity greater than 2. But the branch width is the minimum width, the minimum amongst all possible branch decomposition. So that one that we're looking at there is a minimum width branch decomposition of the graph. And the nice thing about a branch decomposition of a graph is that the only thing that you need to know about the graph to describe a branch decomposition is the associated connectivity function. So that if I had that branch decomposition, I don't need to know any more details about the graph other than the associated connectivity function. So you can think of the graph as being nothing more than a oracle for giving me the connectivity function from the point of view of branch width. Branch width doesn't care about anything else. Okay, so, and I think I'm a terrible scholar, but I think that branch width was probably first defined in Graph -10 by Robertson and Seymour. And they originally, in the earlier Graph Minors papers, primarily focused on tree width, but they talked about branch width in Graph -10. And the reason why they switched, at least in that paper, to branch width was that I'm getting ahead of myself, but we'll come to that in a moment. So the fact that branch width depends only on the connectivity function means that, as well as once I've defined branch width for vertex connectivity and graphs, and I observe that I've only used the underlying connectivity function, then it means I can also define branch width for edge connectivity and graphs. That's called carving width. It's somewhat studied, but not as well studied as branch width in graphs, I have to say. And of course, we can talk about branch width for matroids and polymatroids. And of course, we can just talk about branch width for an arbitrary connectivity function in general. So branch width is the way that we define branch width there means that we've got something that works not just for graphs, but works for arbitrary connectivity functions. And that's a nice feature of branch width that doesn't immediately work for other width parameters that you might think about for graphs. So why do I care about this? Well, in Graph Miners 10, Robertson and Seymour proved a theorem, which is that branch width and tangles, and again, if you don't know much about tangles, don't worry, just believe me that tangles are sort of interesting things. But they proved that either a graph has branch width, low branch width, so that branch width at most k, or if it doesn't have if it has branch width greater than k, it means it's got a tangle of order at least k, or something like that. One of the k's might have to be k plus ones, I always forget. But you know, so high branch width guarantees the existence of a high order tangle, and low branch width guarantees the non-existence of such a tangle. And they did it in Graph Miners 10. They did it just for graphs, but it's clear that their result essentially worked for any connectivity function. They were just using facts about the connectivity function, and it was generalizable. So that really made a massive impression on me. Here was something that I think is a genuinely deep theorem. It's not a difficult theorem, getting the tangle branch width duality, but it's capturing something that I think is truly fundamental. And that is being done by people who at the time were interested in graphs, but done in a way that generalizes to arbitrary connectivity functions. And that's saying that there's something going on in connectivity functions that is interesting. That there's enough, even though the axioms seem very weak, being a symmetric submodular function seems a very weak set of axioms, there's enough there to get results like tangle branch width duality. So that's just already talked about that. And then there are then it also tells you more that when a theorem is proved, so when Robertson and Seymour proved the grid theorem for graphs, you think, well, fundamentally, the grid theorem is really a theorem about connectivity functions of graphs. And then that tells you, well, naturally, you can ask, where does that theorem extend to? To what other worlds does that theorem extend to? So again, that's one of the reasons why I think over the years, I've just sort of thought of connectivity functions as being interesting structures in their own right. They somehow become, I managed to. Okay, so now what I'm going to do, so that's a sort of an introduction to the world of connectivity functions and some examples and a bit about why I care. The next bit is that I'm going to go back and talk about some results about bounding branch width, and in different settings depending on where the objects we want to bound the branch width of. So we could ask, if I give you some a class of structures with an associated connectivity function, so these could be, vertex connectivity in graphs, edge connectivity in graphs, matroids, polymatroids, they're the structures I'm talking about. And a given notion of substructure. Now, that's something to think about now, because we're going to talk about the notion of substructure. And again, I have a minor obsession about substructure too, because if you ask me, no, it's a major obsession. I sort of spend a lot of time worrying about things like this. But if you ask me, is graph theory a subject? I'll say my answer is often no. It's numerous subjects. But if I want to know when does graph theory become a subject, I think it's then I think it becomes a subject when you tell me what your notion of substructure is. So if you're a graph theorist and you say, oh, well, for me, substructures are minors, I'll say, terrific. I really like that because I'm a Matroid theorist and that works for me as well and things like that. And then all of a sudden, once you're in that world, you're in the world of what you can regard as a genuine subject where there's a sort of broad themes and interrelated, the results sort of are all connected to each other. But if you tell me your notion of substructure is subgraph, then you've got just ordinary subgraph, then you've got something like what I tend to call Hungarian graph theory, which is sort of the Szemerédi Erdos school of graph theory. And if you tell me that your notion of substructure is induced subgraph, then you've got another world of graph theory as well. And then and those worlds are sort of clearly related, but they clearly sort of somehow, and then they become, so I think if you want to know what subject's about, you know, think about what the notion of substructure really means, and that tells you a lot more than just what the definition of the object is. Okay, got that little thing off my chest. So one thing so if you've got a notion of substructure, and here's a natural problem, you may or may not care about it, but it's a problem that you can certainly study, is what are the minimal obstructions to having branch width k for some fixed k? Minimal obstructions of branch width 10, or at least bound their size. Here for a Matroid theorist, the natural notion is that of minor, and the minimal obstructions are excluded minors. That's the natural thing that a Matroid theorist would think about. And here's a theorem that goes back quite a while of Jim and Bertz and Neil Robertson and myself back to 2003. I discovered somewhat to my unease when I looked it up in the literature. It says, if I give you a minor minimal excluded minor, so a minor minimal matroid that has branch width greater than k, then it has 6 to the k minus 1 divided by 5 elements. That's a pretty small number in the way that you expect these things to grow. So for example, branch width 3, 6 to the 3 minus 1 divided by 5 is not a huge number. And so that's quite a satisfying result. And somehow that's saying that there's a sort of some control over there. And given that in matroids, infinite anti-chains of matroids are all over the place, the fact that it's even finite is somehow sort of interesting here, because that's just a result for general matroids. Okay, now I would have liked to have spent a bit of time talking about the technique of that proof, but I'm not going to have time to. But it's not, the thing about it is the proof is short. The paper's only about 5 or 6 pages long. It's got a couple of key ideas, and once you understand those key ideas, it's sort of straightforward as to what you have to do. You get as a corollary of that if you're an excluded minor for graphs of branch width the most k, then I've got the same number of elements. I suspect that these days a stronger bound is known, but I was going to spend some time to look up what's known about that for graphs, but I didn't. But you get that as a corollary because even though vertex connectivity functions of graphs are genuinely different functions from connectivity functions of the associated cycle matroid of the graph, they genuinely are different. They're related in ways, and the class of graphs of branch width k is the same. Branch width the most k is up to some trivial exceptions. I forget exactly what. Is essentially the same as the class of cycle matroids of graphs of branch width k. So you get that as a corollary. But on the other hand, you could just use the same techniques to prove the result for graphs that work for matroids. And then what about, so since that branch width occurs naturally in other settings, what other worlds can we go into where we can think about bounding the branch width of getting a result from, let me see if I can say this coherently. We want to find the minimal obstructions, bound the size of minimal obstructions for branch width K for some other class of objects with associated connectivity functions. And we sort of, well, first of all, you've got to decide what your notion of substructure is. One class that you might look at is the class of all connectivity functions. Just take all of the connectivity functions, and what you need is a notion of substructure that works in this general setting, and that means we have to think about kappa. And so if I give you a connectivity function, I mean, we're all familiar with, anyone who already knows Menger's theorem already knows what this kappa thing is. It's a sort of a generalization, but let's just see if I can say something coherent. If I give you a connectivity function on some set S, and then I've got a partition AZ B of S, then kappa AB is the minimum of the connectivity of all sets that contain A but avoid B. Right, so what you're looking at is, if you can think about connectivity in terms of partitions, you're thinking of a partition which has A on one side, B on the other side, and you're looking at the minimum of that. And so that's what kappa is. And of course, if we think about vertex, if you're thinking in just normal graph terms, you know, like in Menger's theorem language, you say that kappa AB is the minimum vertex size of the vertex cut that separates A from B. And so that clearly an important thing. Actually, it's funny, I mean, I find this, I mean, I'm sure all of us here find this a very natural thing, but for many, many years, I taught computer science students who had to do a second year course in mathematics. Most of them, it was the last place on the planet they wanted to be. Mainly they wanted to be in a dungeon eating pizza and sort of in a dark room and programming and things like that. But I would have to teach the max flow min cut theorem and get them to run them, you know, the sort of maximum flow algorithm. I thought, well, I came to the conclusion after many years, yep, you might not be able to get them to understand the max flow min cut theorem, but you can get them to run the flow algorithm by hand on small examples. So that was at least a minor victory. In any case, so we're familiar with, we're all familiar with versions of this. And so you've got the vertex version and the edge version. And Tutt's linking lemma for matroids is a kappa theorem for connectivity functions of matroids. So what it says is that if I give you a matroid, and in a simple case, say I've got this partition AZB of the matroid, and I tell you the connectivity of A is equal to the connectivity of B is equal to K, and moreover, kappa AB is also equal to K, so there's no smaller separation that separates A from B, then I can delete and contract elements of Z and get a minor on A union B that has connectivity K as where the lambda is equal to K. So that's a beautiful theorem and very easy to prove, in fact. So it's clearly this is an important thing. Okay. So why did I say that? Because that gives us a way of defining a notion of substructure for an arbitrary connectivity function. We call it a lesion for want of a better terminology, and we use a down arrow. But what it does is it say, let's take a subset X, and we're going to remove X. So what we're left with is what's S minus X. And then what I say is, what's my in this new connectivity function, what is my connectivity? Well, I'm looking now at subsets of S minus X, and I'm saying that the connectivity of a set S is the kappa from that to its complement in S. Now, I haven't said that very well, and hopefully I'll say it a bit better when I come to an example. But notice it's very simple if we have a singleton. If I just remove a singleton, then once you take X out and you look at a subset of E minus X, then, or S minus X in this example here, then it's just the minimum of the connectivity of A or A union X. So it's very simple in that case. So what are we really trying to say here? So here's an example. I've got a group of people scattered all over the planet. They might be sharing a Zoom call or something, who knows? And what we've got, so the connectivity function I've got in mind is something that's associated with the internet. So for every subset of people with a computer on the planet, there's some connectivity which measures the connectivity to the rest of the world. It's a massive, got a massive size ground set, but you might have, say, 1,000 people. And what they care about is how well they're connected to each other. And what that expresses, so for a subset of those people, they want to know how well they're connected to their friends. Well, the point is, what they're able to use is the rest of the system. So they're able to use the whole big graph. And then, so what you're seeing is that for subset X of people, you'd have to say lambda X is kappa of that set of people to the complement of that set of people in that little community. And so that gives us a connectivity function on this smaller set of people. All right, so a lesion is really just saying that you're just going to a smaller subset, but you're looking at how much connectivity you get between the things in the smaller subset, where we're allowed to use the bigger thing to get the connectivity. Okay, I've said enough about that. I'm not going to make it clarified by going on and on. So, so that gives us a notion of substructure for arbitrary connectivity functions. And I don't know of any other notion of substructure that works in any reasonable way for the class of all connectivity functions, this lesion. And Susan proved in her master's thesis that if you give me an excluded lesion minor for the class of all connectivity functions, then it has at most 3 to the k plus 2 minus 1 divided by 2 elements. This is Susan's theorem, but I'm 99% sure that it was Jim who first realized that this is something that you could do. I don't know if Jim might say later on, but I don't know if Jim had this notion of substructure in mind. But anyhow, I'm pretty sure the idea was Jim's. So this is a theorem that's got a very similar flavor to the one we said for matroids before, but it's a theorem that works for all connectivity functions with a particular notion of substructure, a different notion of substructure than deletion or contraction, it should be pointed out. This is a nice result, but if you would say, oh, could I use this result? Say I'm a graph theorist interested in edge connectivity. Oh dear, how sad, you can't, because when you take a lesion minors, if you're interested in some other class, then taking an lesion minor will typically throw you out of the class. And your notion of substructure better not throw you out of your class. So even though this works universally in some sense, it's not necessarily helpful for particular classes. Having said that, I don't know that there's much known. If I take all matroidal connectivity functions and then I close these things under this notion of a lesion, I get a genuinely bigger class of connectivity functions. And I don't know much about what this class is like. And I mean, we sort of know something because we can use the fact that there exists a matroid, blah, 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 but I don't really have a strong feeling for what's going on in that world. But it is slightly interesting. No, I won't say that because I'll run out of time, so I'll move on. It's just that I think that's these are interesting worlds to think about in terms of their properties. I think a lot of times graph theorists are actually working in those worlds but whether or not it's a useful thing to sort of somehow ask questions about these objects in their own, think of them as objects in their own right. I'm not sure. Okay, moving along. All right, so we've got an excluded minor theorem for elision in general connectivity functions, one for matroids, one for vertex connectivity in graphs. What about edge connectivity in graphs? I used to think the notion of immersion minor was very unnatural. Now I think it's the most natural notion that you could ever imagine. That's because I've immersed myself in it for a while. That was a terrible pun, sorry about that. So the natural notion of substructure for edge connectivity in graphs is immersion minor. And here one's allowed to delete edges, delete vertices, and split vertices. Now, if you're not familiar with this, I'm not going to say anything more, but there is a natural notion of substructure there. One thing that's a little bit funny when we come to thinking about the associated connectivity function is that if I give you edge connectivity in graphs, the associated connectivity function is a connectivity function on the vertices. If I delete an edge from the graph, I'm changing the connectivity function, but I'm not changing the set of vertices. So what's actually happening is I've got a notion of substructure for edge connectivity in graphs, but that notion of substructure doesn't sort of induce, it does induce some sort of substructure, but notice you're keeping the same ground set. You're keeping the same underlying ground set. So in this world, if we're thinking about this, we say, oh, okay, that means if I'm thinking about this in a general sense, maybe I've got to allow something to be a proper substructure, but having the same ground set. And there's no reason why not. It's just something that you have to think about. And that's just the comment there. So Jasmine Hall has been doing a PhD with me and eventually proved this theorem that if I give you an excluded immersion minor for the class of cubic graphs of carving, remember carving width is just branch width for each connectivity of graphs. If I give you an excluded immersion minor for the class of cubic graphs of carving width K, then G has at most that many vertices. So that's, well, okay, good on you, Jasmine, but that number's pretty big. But it was the best that we could come up with. And it's a bound, and it's a surprise, perhaps it's a surprise. I'm sure that the true bound is quite a bit better than that, but, and that's for cubic graphs. And what about graphs with higher degree vertices? And then, well, that's sort of work in progress, doing similar theorems for graphs with higher degree vertices. But so what we've got now is we've got three different theorems for three different classes of connectivity functions, because we really are talking about the connectivity functions, because branch width is determined by the connectivity function. And the question is there a way of unifying? And I think I'm going to skip over this slide, except to say that the proofs are all similar. And what you do is you just simply take the proof that's given in the original paper that with for branch width of matroids, see the main ideas and try to transfer those ideas into your new setting, right? And but I just won't have time to talk about them. I was hoping to say a little bit about it. So the question is it possible to find a setting that unifies the proofs of these three theorems? So rather than independently go and play the same game in different settings, is there a general theorem for connectivity functions that finds a unified setting, in which case, and it would say, oh, okay, so I've got my favorite class of objects with my favorite notion of substructure, and I want to bound the size of minimal obstacles. Is there a general theorem for connectivity functions that just gives me necessary and sufficient conditions for what I have to do and what I have to check in my class? And that was the goal, to sort of find such a thing. The upshot is that led us to this. Now, that slide, I sort of look at that slide and I'm embarrassed by that slide because it's got too much stuff on it. But let's see if I can make some of it digestible. So what we have to say, so what have we got? We've got connectivity functions, different classes of connectivity functions, and all our examples is we've got different notions of substructures in our different examples, and they're all sort of genuinely different notions of substructures. So what sort of class, what do the associated classes of connectivity functions look like? And this was our attempt to sort of axiomatize, come up with axioms that characterized what would be a reasonable thing, a reasonable analog of some sort of minor closed class of connectivity functions where somehow the notion of minor gets incorporated in there. When I say mu t is a connectivity function, I just say that just means it's a connectivity function mu with the ground set t. So let's see what's going on there. So the first axiom says, so now we've got a partial order on our connectivity functions. The first axiom says that if you know that you've got to respect ground sets, so the ground set has to be a subset, but not a proper subset. Notice that so you can be genuinely, you can have the ground set the same, but be genuinely strictly less than in the partial order. And C2, C3, and C4 are sanity check axioms, so I'm not going to talk about those. They're ones that you sort of just need to make things work. And also we couldn't think of any interesting examples where these didn't hold, so we sort of chucked them in, but there's nothing unusual about those. But the C5 is the interesting one. It says, if I'm telling you that mu of t is a substructure of lambda s, and then I'm looking at x as a subset of t, then what I've got to tell you is that mu of x is less than or equal to kappa lambda x t minus x. In other words, what's happening is my value of the subset x in the smaller thing is at most the kappa corresponding kappa value in the bigger thing. And that seems to me the absolute important one. And why is that? So there, I've repeated that again. And what that's saying, even if you didn't digest it, what that is a way of saying that in a sensible notion of substructure, one should never gain information. You should never gain connectivity when you move to a substructure. And so I feel that, and in general, if you tell me that, oh yeah, I've got a substructure of Blatt, but somehow there's more information in my substructure than there was in Blatt, I'd say go home and come up with a different notion of substructure. It's just sort of a general metaphysical belief. Can't believe anything else could be reasonable. So that there's our definition. Here's a monotone order of connectivity functions, and it's got these properties. And then one asks, okay, and let's go quickly whiz through some examples, because all of the natural examples give us monotone orders. Matroidal connectivity functions, so if I tell you that it's just that if the matroids are minors, then that gives me a monotone order. Similar for vertex connectivity functions of graphs. All connectivity functions with a lesion clearly give me a monotone order on the whole class of things. And edge connectivity functions also give me a monotone order, but I mentioned it before. When you delete an edge, you're not necessarily removing any element from the ground set of the associated connectivity function. So that's you're not changing the vertex set. So that means if we want to incorporate edge connectivity, we have to allow the possibility that ground sets stay the same. And again, I think this is interesting, but maybe I've just got bad taste. And in a way, that's the theme of this talk, by the way. I said it right at the start. It's a question of, are these things interesting, or, do I have bad taste? I worry about that sometimes. No, I've got terrific taste. I'm confident.
Geoff?
Yeah.
Can you get anything from the weak order or quotients where you fix the ground set in Matroid?
Yeah. I'll come to that in a moment. Actually,
okay.
that's yeah. So where are we? So the point is that once we have the definition of monotone order, we can come up with a theorem. And it's too technical to state here, but it's not terrifically technical. If I wanted to make the focus of this talk just that theorem, we could have plenty of time to talk about it, but I haven't. But what it does is it gives you sufficient conditions to bound the size of a given. So it basically gives you sufficient conditions to say, oh, you give me your particular class of objects. This is what you have to do. And if you've done those things and checked them off, you've bounded the size of your minimal objects that are minimal with respect to having branch width greater than k. And all the branch width theorems discussed earlier can be derived as corollaries of this general theorem. So that's somehow the point of that generalization. But again, is it worth it? Is it worth doing all of that? Because it was quite a lot of work. It's quite a lot of work doing the general theorem, and it's probably, you haven't saved yourself any work, probably not at all. But somehow I sort of think it is. It gives you a slightly somewhat different way of thinking about these minor orders. And it sort of leads to some questions that you might ask. For example, Peter, you could ask, what's the richest monotone order of matroids? And so you're just looking at matroidal connectivity functions and you say, what's the richest one of these? It contains the minor order, but it also contains certain quotients and lifts, but not all quotients. Because when I take a quotient, so if you don't know what a quotient is, a quotient of a matroid is an elementary quotient is you take your matroid, you add an element x and you contract x, and then that gives you a new matroid, and the second matroid is a quotient of the first. Clearly you can have a quotient where you've gained connectivity in certain places because that element x gives you the opportunity to gain connectivity. But is it interesting to think about, the class of quotients where you have not gained connectivity, and they would be quotients that are compatible with being part of a monotone order? And is this an interesting order, and is it something interesting to think about? And the answers to all of these questions is I don't know, and I will leave it at that. Thank you very much.
Thank you. We don't usually do applause in the seminar, but I'm sure that if you look at the participants list, you'll see a bunch of the images of claps. All right, so now would be a good time for questions. And in a minute, I'll stop the recording for any other questions that you don't want recorded.
One other way you could use a lesion is to use connectivity intertwining to get, like, so if you've got connectivity intertwining in your class and I know something about the excluded minors for a lesion, then I can get a bound on the excluded minors for any class. So for vertex connectivity, matroid connectivity, rank width, edge connectivity, for all of these things, if I've got as long as I can do connectivity intertwining, I can take the lesion result and I can turn it into a minor result. But you get obviously bad bounds, but
yeah.
Can you understand the lesion in terms of polymatroid connectivity? Because you're not breaking out of the class if you're doing that.
No, if I do a lesion, there'll be some other polymatroid that.
Right, but can you tell me what that polymatroid is? If I give you a polymatroid and I tell you what I want to elide, can you stay talking about polymatroids and get from one to the other?
Yeah, I've only ever thought about that problem in certain special cases. So here's a strange theorem that, and I thought this theorem would, and it may not be answering your question, Peter, but I thought this theorem would be interesting and useful, is that every unitary connectivity function is essentially up to a scaling, is essentially the the connectivity function of a self-dual two-poly matroid. Now, there's a natural notion of duality for two polymatroids. So in other words, you get, even though unitary connectivity functions, by the way, for those who don't know, unitary connectivity functions means the connectivity of singletons is equal to 1, or at most 1, but in a non-trivial case is equal to 1. So every unitary connectivity function, it's sort of there's this. And now unitary connectivity functions are much bigger class than the connectivity functions of matroids. And then yet self-dual two-poly matroids are a much smaller class than the class of two-poly matroids, and yet they also contain. And then, you know, I thought that would help me understand, but then I couldn't find, I think I was looking for a natural relationship between a lesion from the connectivity function and this gives you some order on these self-dual two-poly matroids, right? That when you lead something, and I just got confused by it. And that's the only thing I know about that question, that I thought about that specific version of it. Does that make sense, Peter?
Yeah, so I guess it's not that, I can't remember the name of the operation you do where you contract, half delete, or you're probably not maintaining self-duality when you're doing that. All right.
I think Susan called it squidging.
Squidging, okay. Yeah.
Yeah, I don't think it's quite squidging. It's something funny there's funny going on there.
So are two-poly unitary connectivity functions closed under a lesion?
Yes.
Okay.
Yeah, and the way to see that is just look at a singleton. It can't gain connectivity under a, yeah.
I was wondering if the same sort of dilemma works in this context, where you can have many different polymatroids with the same connectivity function, but in terms of self-dual, two polymatroids with the same unitary connectivity function, say.
Oh yeah, now that's actually, I don't know the answer to that straight off, but that's when that sort of thing becomes interesting, I think, because somehow being self-dual two-poly matroid puts you into a relatively highly structured class of two-poly matroids that you might say, I can think about these objects. And I don't know the answer to that, but I suspect it's probably true. I suspect that once I give you a unitary connectivity function and I say that might be a canonical construction that does it uniquely, but I could be lying. So that's just my gut feeling, yeah.
Can you count connectivity functions?
I've got a master's student who's been working on that. So well, one of the things is probably the sensible thing is to start by counting unitary connectivity functions, and you could actually, and what he's done is he's actually looked at, and then counting connectivity functions, what you want to do is you want to have a notion of modular cut for connectivity functions. Mm-hmm. And so he's done a theorem that says that the reverse of a lesion is to have, so you could sort of define modular cuts for connectivity functions, and in quite a general setting, each time you define a modular cut for a connectivity function, you can get a bigger modular. But there's one specific type of modular cut, and I just forget exactly what the property was, but it's a natural property, and this corresponds to a lesion. So you can work your way up by looking for modular cuts in a connectivity function and using those to count them. And he's a computer sciencey type of person, so hopefully with that and a bit of work, you could count them up to, at least up to size 8 or 9 or something like that. Uh-huh.
Yeah. All right, thanks again, Geoff. I'll stop the recording.